All right, guys, so we were plotting our x and y points for this function, and we had just plotted 8. And so remember, when you're plotting these, if you do want to use your calculator, just go ahead and make sure you put parentheses around your denominator. That way you end up with the correct order of operations. So if I then go to plug 6 in, I'll end up with 2 on the bottom in the denominator. So 2 divided by 2 will give me 1, plus 3 will give me 4. So I'm going to go ahead and plot these values. If I go over 6, I'm up 1, 2, 3, 4 right here. And then at 8, so 5, 6, 7, 8, I'm right about here at 3.5. So this particular rational function graph is going to follow this trend and then hug those asymptotes along the side there. And then if I plot 2 down in the denominator, I will have 2 minus 4, so negative 2. And then when I divide 2 by that, I'll get negative 1, plus 3 will give me positive 2. So I'll be over 2 and then up 2 here. And then if I plug 0 in, I'll have 0 minus 4, so negative 4. 2 divided by negative 4 will give me negative 0.5, plus 3 should give me 2.5. So if I'm at 0, I'll be right up here, 2.5. So this particular graph is going to come along through those points and then down this way to touch or to come close to touching the asymptotes. Then the last thing we need is to identify the domain and range. So my domain is just that my x values cannot be 4. My range is that my y values cannot be 3. And then if I wanted to be specific about how this graph is different from my parent function 1 over x, there are 3 changes. There's a vertical stretch because the 2 up top in the numerator is kind of increasing how quickly this graph grows. Then there's a horizontal shift or a translation, and that translation brings us right by 4. And then we have a vertical translation, and this vertical translation or shift is moving the graph up by 3. So that's it for this particular graph. Then let's go ahead and take a look at graph number 7. So with this graph, just like before, we want to identify what our vertical asymptote and what our horizontal asymptotes are. I usually like to do this before I pick points. That way I have a clear sense of what I want to pick above and what I want to pick below. So my vertical asymptote here is going to be x is equal to 1 because I can't plug 1 into that denominator. Then my horizontal asymptote, remember there's really a 1 hanging out right in front of that x. So if I divide my leading coefficients here, 7 by 1, I'm going to have a horizontal asymptote at y equals 7. So I'm going to go ahead and plot those asymptotes at x equals 1. That will be, oops, I can't get that to be quite straight. That's going to be my vertical asymptote right there. And then my horizontal asymptote is going to happen at 7. So I'm going to go ahead and loop this around. And then 7 is right here. So my graph's going to be shifted that way. So now I'm going to go ahead and pick my points, my x and y values that will allow me to plot this graph. So this is going to come here. And I'm going to pick above and below 1. So let's pick 2 and 3, and then let's pick 0 and negative 1 for values that are going to be above and below. So you want to get some practice plugging these into your calculator. So up above, I'll have 7 times 3 minus 1. Divide that by 3 minus 1. And I get 10 for this point. Then when I plug 2 in, 7 times 2 minus 1 divided by 2 minus 1, I get 13. 0 is my vertical asymptote, so I won't plug anything in there. Then I'll have 7 times 0 minus 1 divided by 0 minus 1. So I get 1 here. And then when I plug negative 1 in, 7 times negative 1 minus 1 divided by negative 1 minus 1, I end up with 4 as my result there. So let's go ahead and plot these. If I do 3 first, 1, 2, 3 is here, and then I'm up at 10. And then 2 is up at 13. So this piece of the graph kind of comes down like this. And then on the other side, I have 0, 1, and then I have -1, 4. So this graph is kind of coming along this way, going through those 2 points and down here. And then I can go ahead and talk about the domain and range. So my domain is that x cannot be 1, and my range is that y cannot be 7. So for this graph and the other more complex graphs, we're not going to compare them back to the parent function. We'll just do that when we have the basic translation, so a stretch and then 1 horizontal shift or 1 vertical shift. So that's it for problem number 7. All right, guys, we have 2 more graphs on this review sheet, and these both come from the slightly more complex rational functions that we encounter in section 8.3. So these ones are just going to require us to do a little bit more thinking when it comes to where our asymptotes come from. So here we can end up with quadratics both in our numerator or our denominator. So our graph here is that y is equal to 10 divided by x squared plus 4. So in order to find my vertical asymptotes, I want to take a look at what's going on down in the denominator here, so x squared plus 4. And I want to think what could cause that denominator to be equal to 0. So in this case, what I find is that if I subtract over that 4 and then try to take the square root, this would be an imaginary result. So if I have an imaginary result, I don't have any vertical asymptotes. So I don't need to draw in any up and down vertical dashed lines. I'm going to be able to plug in any x values. Now I want to make sure that I'm careful that I always check that, because if I had x squared minus 4 on the bottom, it would be a different story about my vertical asymptotes. So then I get to move on to my horizontal asymptotes. So in this case, I want to compare what's going on with my exponents in the top part of my fraction and the bottom part of my fraction. So here my exponents are larger on the bottom. The square is larger than just the constant up above. So whenever that occurs, I'm going to have a horizontal asymptote at y is equal to 0. Now, anytime they're equal, I'll divide my leading coefficients, and then anytime they're bigger up on the top, I won't have horizontal asymptotes to graph. So I'm going to go ahead and draw in a flat dashed line at 0 to show that I have that horizontal asymptote. So I can predict that my graph is all going to be up above that asymptote or all below for this kind of work. So then I'm going to go ahead and pick some values, and it doesn't matter which ones I pick, but I usually like to do some that are negative, 0, and then some that are positive, so I can kind of see the symmetrical shape. So here, let's go ahead and pick, let's do -2, -1, 0, 1, and 2. Now 0 is probably the easiest thing to plug in. So if I plug 0 in, I'll just have 4 on the bottom. So that y term is going to be 2.5. So I can go up. 2.5 is right about there. If I plug 1 in, that's going to become 5 on the bottom. So this will be 2. And that would be the same thing as if I plugged in -1, because it's going to get squared. And then I have -2. So when I plug those in, I'm going to get 8 on the bottom. So for -2 and +2, my result is going to be 1.25. So it's kind of right just above the 1. So this graph is going to have sort of a little hill shape in the middle, and then is going to really closely approach the axis on both sides. So when I want to talk about this domain and range, I don't have any restrictions on my x values because I don't have any vertical asymptotes. So this domain is going to be all real numbers, which you can also say using this fancy R shape. And then our range is going to just be that y is greater than 0. So it's not that it's not equal to. In this case, we want to describe that I'm only going to be up in the top 2 quadrants. But then also notice that the largest value on this graph is 2.5. So I want to say y is less than or equal to 2.5. And I can combine this information into one single inequality that looks like this. So that's my first 8.3 graph, and then we just have one more. So you certainly won't have more than 2 of these kinds of graphs to manage. So once again, I want to take the same approach where I check and see what is going on down in the denominator and up in the numerator to identify my asymptotes. So first I'm going to look at this x squared minus 16, and I'm going to set it equal to 0. This will become x squared equals 16, which tells me I'm going to have vertical asymptotes at plus and minus 4 because both of those values would cause my denominator to be 0. So I'm going to go ahead and find negative 4 right about here, and I'll sketch in that vertical asymptote. And then I'm going to find positive 4 over here and sketch in that vertical asymptote. Then I need to consider how the exponents compare. That's my vertical asymptote there. As far as the numerator and the denominator. So in this case, both the top and the bottom of my fraction have equal valued exponents, which means I'm just going to divide the leading coefficients. So when I divide, I will end up dividing 3 over 1. So I'm going to have a horizontal asymptote at y equals 3. So go ahead and draw a horizontal line this time in at 3 on your graph, so right here. And then I can start picking points to plot. And my recommendation is that we pick some on each side of our vertical asymptote. So we're going to want some that are smaller than negative 4, some that are in between negative 4 and positive 4, and then some that are bigger than positive 4. So that way we get a full picture. You're also going to want to plug these into your graphing calculators to make sure you're sketching the correct trend. So negative 4 and 4, I'm going to pick some on each side. So let's do negative 5 and negative 6. How about negative 1, 0, 1, and then 5 and 6. Picking symmetrical values is always good because then you're going to get some of the same out when they're squared. So I'm going to plug negative 6 in. 3 times negative 6 squared. And then I'm going to divide that by negative 6 squared minus 16. So I get out 5.4, which also means that I'll have 5.4 when I graph 6. When I plug in 5, I'll have 3 times negative 5 squared divided by negative 5 squared minus 16. And that gives me 8.3. which will also be what I get when I plug positive 5 in. Then when I do 1, 3 times 1 squared divided by 1 squared minus 16, I get negative 0.2, which will also be what I get when I plug in positive 1. And then when I plug in 0, I'll get out 0. So you want to make sure that you can move through those problems efficiently, plugging them into your calculator to get those y terms out. So now when I plug negative 6 in, that's at 5.4, so right about here. Negative 5 is up here at about 8.3. And so then I can connect those points following the trend and the restriction of those asymptotes there. I have negative 1, negative 0.2 right here, 0, 0, and 1, negative 0.2. So these guys kind of are going to look similar to what we would expect from a parabola with the way they curve down. Then I have 5 and 8.3, so very symmetrical. 5, 6, 7, 8, and then little 8.3 right there. And then at 6, I'm up here at about 5.4. So this is going to be a mirror image of what we graphed over on the left, and it's just going to follow the shape of the asymptotes without ever crossing them. So for these, we just want to be able to identify the domain. We're not going to have to worry about the range. But my domain is just what my x values cannot be equal to. So in this case, they're not going to be able to equal positive or negative 4. So that's our most complicated rational function graph that we can come across. Next up, we're just going to have our operational material, so our multiplication, division, addition, subtraction,